Jai Hind and very good morning. Myself Dr. Tarun Bhardwaj, and today I'm just covering my first complex topic 1 of the additive manufacturing. The subject code is KME 071. Myself Dr. Tarun Bhardwaj, Assistant Professor, Department of Mechanical Engineering, Ajay Kumar Garg Engineering College. So let us start with this design for additive manufacturing. So as we have already talked about the additive manufacturing, that what actually the additive manufacturing is. Additive manufacturing is basically the process of generating any 3D CAD model by using the layer fashions. Okay, so we will discuss over here about the design for additive manufacturing. So first of all, we will just see what is the outline over here. The first one is the motivation. Second one is the design for manufacturing assembly. Then AM unique capability. Then core concept and the objective, exploring design freedoms, and the design tool for the AM. So let us start with this motivation, means how that motivates us कि हम लोग इस basically इस topic को क्यों पढ़ रहे हैं. Okay, what motivates us for this design for additive manufacturing, because this is not included in our syllabus. Okay, so let us start with this motivation. Design for manufacture and assembly, that is DFM, has typically mean that designers should tailor their design to eliminate the manufacturing difficulty and minimize the manufacturing, assembly, and the logistic cost. So over here, as you can see that the DFM has typically mean that designer should tailor. Okay, so as the additive manufacturing, the purpose of the use of this additive manufacturing is that you can just change your design. You if you found that the end product is not useful to you, okay, if you found that is not suitable to you, so what you will do that you will have to change your design. So in the conventional process, what actually happened that you have to change whole setup for that particular end use product. Okay, but over here in the additive manufacturing, as you can see that you have to change the design, and that design is basically the CAD model, and that CAD model is converted into the STL and finally into the final product. Okay, so however, the capability of the additive manufacturing technology provides an opportunity to rethink DFM to take advantage of the unique capability of these technology. So the unique the capability of this you can say the additive manufacturing is that you can change the design, and that design is basically help you to change your additive means the final end use product. Okay, if you found that product is not up to your, you can say, the expectations, so what you do that you have to change that design, and that design is basically converted into the end use product by using this particular technology. Okay, then as you can see that for hearing aids and the dental alignments, the AM machines enable the manufacturing of tens to the hundreds of thousands of parts, where each part is uniquely customized based upon person specific geometric data. So as we know that this additive manufacturing technology, that is basically it is being used for the, you can say, the customization process. Okay, and basically for, you can say, a very complex products. So additive manufacturing you can use anywhere, but it is mainly being for the your complex objects, and second one is for the customization purpose. Okay, so if we just talk about the customization purpose, so the best example over here is in the medical field, as you can see, for the hearing aid and the dental lineup, because we know that we all have a different kind of a shape of a body. Okay, so if you can just see the hearing aid, so everyone is having their own, you can say, the shape of your ears, so you just require a different kind of the hearing aids. But if we just go to the market, you will see that you are getting only you can say the specific type of the hearing aid over there. But if you just require that hearing aid is according to me, okay, so how you can just get that? You can just get that by using this additive manufacturing. You can just have a scan of your ear. Okay, and after that scanning, you can just convert that scan into the CAD, and after that you can just convert into the STL, find out your product. Okay, same with the dental aligner, same with your you can say your orthopedic implants, same with your maxillofacial craniofacial implants. Okay, so this basically the motivates us that you have to read this particular subject, the design for additive manufacturing. Okay, So AM machine enable the manufacturing of tens to hundreds of the thousands of the parts. Okay, so in this case, the aircraft component AM technology enables the low volume manufacturing, easy integration of the design change, and at least a piece part reduction to greatly simplify the product assembly. Okay, so as you can see, if we just talk about the aircraft component, so AM technology enables the low volume manufacturing, easy integration of the design changes, and the least piece part reduction to greatly simplify the product assembly. Means if we just require that, we just talk about some assemblies. So what actually happened in the assemblies, that sometime there may be a chance that that assembly will fail due to the you can say the nut and bolts you are using, or the welding you are using. Okay, but if we just go for a simple, you can say, if we just go for that, if we just required a end use product in a one go, okay, without any, you can say, assembly process, so that will be beneficial to you. Okay, so that can be only done by using this additive manufacturing. Okay, so the unique capability of this additive manufacturing technology enable a new opportunity for the customization. Okay, as we know, so in product performance, multi-functionality, and lower overall manufacturing cost. Okay, so this is about the motivation to us. Then these are also some unique capabilities that also motivates us. The first one is basically the shape complexity. Okay, so it is possible to build virtually any shape, as we have studied about the additive manufacturing, that you can what you see you can build. Okay, so over here that will suit that the shape complexity, means जो भी आपने देखा है, you can just manufacture that. Okay, either by using the CAD model, or either if you just require to scan that particular you can say the end use product or any model, so you can just manufacture by using this additive manufacturing. Then the hierarchical complexity. Okay, so what is this? So hierarchical multi-scale structures can be designed and fabricating from microstructure through the geometric mesostructure. Okay, means you are having some mesostructure of that, so you can just design the microstructure from that particular you can say the fabrication process, either using DED, either using the powder bed fusion process. Okay, the size is in the millimeter range to the part scale microstructure. Means if you just require to change your microstructure in any particular product, so what you will do that either you are having a geometric data for that, so by using that geometric data you can design your microstructure of that particular product. Okay, then the third is the material complexity. What is this material complexity? Material can be processed one point or one layer at a time. Okay, so over here that the material that you are basically you can say the fabricated, it can be processed at one point or at the one layer at a time. Okay, means in a single time you can just manufacture that particular material. And if you just talk about the additive manufacturing, you can manufacture means almost all type of the material. Means we are having such kind of the facility in the additive manufacturing that you can manufacture any type, means the polymer also, metallic alloys, even the ceramics, okay, composites, you can manufacture in the additive manufacturing. Then the functional complexity. If we just talk about this functional complexity, so the fully functional assemblies and the mechanism can be fabricated directly using the AM process. Means if we just talk about some model, so if you just require some functional model, suppose you just require that we have to create a model for the two-stroke engine or the four-stroke engine, that should be a functional one. So what we just require that we have to create a different color of that particular model, so that we can show where the piston is, where the crankshaft is, where the crank is. So what we just do that we can create that particular functional model by using this additive manufacturing. So that will motivate us to use this additive manufacturing technology. Okay, now we just talk about the design for manufacturing and the assembly. If we just talk about this design for manufacturing and the assembly, so the design for manufacturing and assembly can be defined as the practice of designing the product to reduce and hopefully minimize manufacturing and the assembly difficulties and the cost. As we know that if we just go for the if we just improve our design, so what we can just reduce that kind of the assemblies that we do not desired in our end use product, but we have to go for, because we are having some limitation in our conventional manufacturing process. But if we go for the additive manufacturing, these kind of the limitation we can overcome. Okay, so DFM efforts can be classified into the three categories. The first one is the industry practices. Okay, industry practices including the reorganization of the product, okay, of the product development using the integrated product teams, then the concurrent engineering. The second one is the collection of DFM rules and the practices. The third one is the university research in the DFM method, tools and environment. We will discuss about them in the detail. So first one, that during the, if we just talk about the in the 1980s and the 1990s, so much of the product development industry underwent the significant change in the structuring the product development organization. Okay, so if we just talk about our nearly about the 1980s and 1990s, so what we will see that the product development industry underwent a significant change in the structuring product development. Okay, so over there, the companies like the Boeing, Pratt, Whitney, Ford, they are basically what they are just doing. They are just reorganize the product development into the teams of these, you can say, the designers, engineers, okay, and the manufacturing personals, and possibly other groups, means they are, you can say, the workers, they are basically working over there. And these teams have 100 or even 1,000 of the people. So how can we just organize them? How can we just design that particular system over there so that we can just structure everything? Okay, so that we can just do over, because if we just talk about the assembly line, so in the assembly line we are having a different kind of the machines we have to go for. Okay, so we have to create a structure for that over here you have to go for the machining, over here you have to go for some forming process. Okay, so we have to means design and everything over there in the particular you can say the tool room. So for means to you can say to reduce that particular process, or to you can say means how can we just overcome by that particular process, we can use this additive manufacturing, so that your process are basically being reduced over there. Okay, it means that assembly is basically being reduced over there. Now the idea was to ensure the good communication among the teams, so that the design decisions could be made with the adequate information about the manufacturing process, factory floor capabilities, and the customer requirement. Okay, so we have to see that what manufacturing process you are using, what factory floor capabilities you are having, means how many numbers of the personals you are having over there, those who are working over there, and there basically the what is the requirement of the customer, means either they just require the your product very you means if they require the product very early, so how you just require number of the labors, so how can you just introduce that number of the labors for that particular process? So that is quite difficulty over there. So we have to design such kind of the thing in the design for manufacturing and assembly. Second, concurrently the manufacturing engineers could understand the decision rationally and the start process planning and tooling development to prepare for in progress design. Okay, then the second category of this DFM work is that the data of the DFM rules and the practices is best exemplified by the handbook of the product design and the manufacture. In the 1986 edition of this handbook of the product design of the manufacture, what we'll see that over it is the book of 950 pages with the detailed description of the engineering, materials, manufacturing process, and the rules of the thumbs, means what are the rules that we have to use for generating any products for any you can say the industries. So there are some rules, there are some engineering materials, there are some manufacturing process. So this is the handbook that is being made, means how you can just manufacture that particular product. That is a 950 page book. So extensive example of the good and the you can say the bad practices are offered for the product design for many of these manufacturing process, such as molding, stamping, casting, forging, machining, and the assembly. Okay, so as you can see that you are having these kind of the process. So so these, there are some good and the bad practices that are offered for the product design for these particular you can say the molding, you have to do for the molding, then you have to go for the stamping, then you just go for some casting, then forging, and after that what you will see that you have to assemble all the components that you are just manufacturing by these, by using this stamping, casting, forging. Okay, so then the third is basically the university research, that is during 1980s and 1990s started with the development of tools and the metric for part manufacture and assembly. Okay, So what we see that some universities have basically come into this picture for using this design for manufacturing and assembly, and they started the development of the tools and some metrics they have just defined that for the part manufacturing and assembly, that it means they have just developed some codes, okay, so that you can just do if you just require to manufacture some nut and bolts, so they have just defined some kind of the metrics for that. That's these are basically the bolts of some specific you can say a unit, okay, so that that can be used everywhere. If you just if some company is making some nuts and if some company is making bolts, so you can just do the assembly for that, okay. So the Booth Royd and this Dewhurst toolkit is probably the most well-known example, and the main concept was to develop the simple tools for designers to evaluate the manufacturability of the design, okay. So the concept is basically to develop the simple tools for the design to evaluate the manufacturability of design, so that they can manufacture these particular designs. For example, injection molding, if we just talk about, so DFM tools were developed that ask designers to identify how many undercuts were in that part, okay. So this is basically the example. Now if we just talk about this AM unique capability, so let us discuss in the details that will basically motivate us for this basically studying this particular topic. First one is the shape complexity. In AM, the capabilities to fabricate a layer is unrelated to the layer's shape, okay. So that is not related to the layer shape. For example, the laser in the wet photopolymerization, the powder bed process, can reach any point in a part's cross section and the process material there, okay. So that actually the laser we are using the wet photopolymerization process also, and we are also using that laser in the powder bed fusion process. So we know that if we just talk about any you can say the complex object, so what you will see that your laser can be you can reach at that particular point where you cannot do that by the conventional process, okay. So as such, part complexity is virtually unlimited over here, and this is in the stark contrast to the limitation imposed by the machining or injection molding, two common process, okay. So that you can not done by your even CNCs also, or even by your moldings, that you can manufacture by using this AM, okay. Then in machining, the tool accessibility is a key limitation that govern the part complexity. If we just talk about the CNC machining also, so over there if you are having some deep grooves over there, so what you will see that your either your tool will not reach over there. So the tool reachability is also the limitation in the CNC machinings. That is basically the limitation over here additive manufacturing, because you are manufacturing any component or any product by using the AM process. Over here what actually happened that a layer is manufacturing over the other layer, so your basically the complexity that you are having in your product is basically being reduced, or you can overcome that basically the complexity. So if we just talk about injection molding, the need to separate the mold pieces and eject the parts greatly limits part complexity, okay. A related capability is to enable the custom designed geometries in production using AM. It does not matter if one part has a different shape than the previously produced part. So if we just talk about the additive manufacturing, so over here additive manufacturing is free from that you are having some design or you have to manufacture another design on that. But if we just talk about the injection molding, or if you just talk about your casting process, so what you are having that if you are making any two parts, so you have to match them, okay, so that your assembly can be completed over here. But over here that is not in the additive manufacturing process. Furthermore, no hard tooling or fixtures are necessary, which imply that lot size of one can be economically feasible, okay. So this is tremendously powerful for medical application, for example, since everyone body shape is different. As I've already told you that we all are having a different kind of the body shape, we are having a different kind of a cross section of our bones, or you can say our body parts. So what actually happened that when you just go to the doctor, or if you are having some accident, then what they used to do, they used to implant the things in your body, okay. So but that basically suits you or not, that is depending upon your body. But if you just go for the additive manufacturing, so you can just scan that particular part and make that particular part by using this additive manufacturing, and that definitely suits your body, because that cross section area or that shape is basically according to your body. High stiffness and the low weights are desired typically with AM, the capabilities to enable to put material where it can be utilized best. So over here, what you can just do, you can just do the topology optimization also. If you are having a facility for the topology optimization, so by using some FEM software, you can do that. You can just remove the basically the material from there wherever it is not necessary. That we will see in our material complexity also. Now if we just talk about this hierarchical complexity, so similar to the shape complexity, AM enables the design for the hierarchical complexity across the several order of magnitude in the length scale. As I told that if you just required means some you can say you want to change your microstructure, either you just require the columnar structure or you just required some long dendrites over there, so you can just do in additive manufacturing. This includes the you can say the nano microstructure, mesostructures, and the part scale macrostructures. The ratio of unmelted carbides to the resolidified carbides within the TI matrix is controlled by using the lens process parameter. You can just see that these are basically the UMCs, these are the unmelted carbides, and over here you can just see that is the RSC, that is the, you can say, the resolidified carbides over here. So you can just change that particular microstructure by using the process parameter of the additive manufacturing, because you are having that means the power over here there, that either using the laser power or by using some the scan speed, the energy density can be controlled. Okay, so if you are just controlling that energy density, your microstructure will change, and that you can do in a part only. That is not possible by any other process. Okay. So one set of the process which has been studied extensively with respect to the hierarchical complexity are the DED process. And in lens, for instance, the nano microstructure can be tailored in particular location by controlling the size and cooling rate of the mild pool. Because if you just talk about the DED process or the lens process, so what actually happened, that is totally defined, but they are basically totally depending upon the, you can say, the cooling rate of that particular product that you are basically particular material that you are basically depositing over there. So if you are increasing that you can say the rate of the cooling rate, so the microstructure will change. Okay, so if you are having a high laser power, so you means that you are giving the more energy density over there. So when you are giving the more energy density over there, that means the microstructure is different from that you are having the less energy density. So you can just change with respect to your microstructures. So as a result, the size and the distribution of precipitates, nanoscale, and secondary particles microscale can be changed by locally modifying the laser power and the scan rate. Then function complexity. So when building the part in additive manner, one always has access to the inside of the part. The two capabilities are enabled by this. First, by carefully controlling the fabrication of each layer, it is possible to fabricate the operational mechanism in some AM process. Second, the components have been inserted into the parts being built in the wet photopolization, ME, PBF, and sheet lamination and other AM processes. Okay. So in the construction of the functional prototypes, it is often advantageous to embed the components into the part while building them in the AM machine. This avoids the post-fabrication assembly and can greatly reduce the number of separate parts that you have to fabricate and assemble. As you can see, the embedded systems we just talk about. So over here, what you can do, you can just you have to create some assembly in the embedded system. But if you just go for the additive manufacturing, you don't require any kind of assembly. You can just manufacture in a one go. As you can see, in example, it is possible to fabricate the VP devices with a wide range of the embedded components, including small metal parts. That can be bolt, nut, bushing, electric motors, gears, silicon wafers, printed circuits, and the strip sensor that you can manufacture in one go. Okay. As you can see over here, this is a SolidWorks CAD file design, and that STL imported to the 3D light here, and the stereolithography, substrate process, and clean. After that, you are getting the electrical component placed where use is required. Then conductive ink traces dispensed and the heat that is cured at 125 degrees Celsius. So this is basically the fabrication of the magnetic flux sensor using the VP or the right. wet formulation and the diatrite. And this is basically taken from the AKGEC Center for 3D Innovation and at the University of Texas. Now, if we just talk about the material complexity, so many EM technology enable the changes material composition gradually or abruptly during the build process, and new application will emerge to take advantage of these characteristics. Okay, so the concept is basically over here, the functionally graded material is the heterogeneous material, means you can just use 2 or more material that has received the considerable attention, but the manufacturing useful part from these material often has been problematic. Okay, so consider a turbine blade for the jet engine. I will just see the example of this. The outside of the blade is basically must be the resistant to the high temperature and very stiff to prevent the blade from elongating the significantly during the operation. You will just see कि आपको क्या basically करना है, that you have to create such kind of blade जो कि आपके high temperature resistance हो, ठीक है, and the blade root must be ductile and have a high fatigue life. Okay, तो उनकी life भी बहुत अच्छी होनी चाहिए, ductile भी होना चाहिए. So blade interior must have high conductivity so that blade can be cooled. Okay, and this is the example of the part with complex shapes that require the different material properties in the different regions. So that can be done by using this additive manufacturing. Now, if we just talk about this core DFM concept and the objectives. Okay, so if we just talk about the this in context to the DFM. So what we just see that we believe that the objective of DFM should be that to maximize the product performance through the synthesis of the shapes, size, hierarchical structures, material compositions subject to the capabilities of AM technology. So to realize this objective, designers should keep in mind several guidelines when designing the product. So these are basically the, you can say, the guidelines over here. The AM enables the usage of complex geometry in achieving the design goals without incurring time or cost penalties compared with the simple geometry. Okay, so if you just talk about some complex geometry, so what we will see that for that complex geometry, if we just talk about the CNC machining, so in that particular CNC machining, you have to generate the different kind of the codes. Or if you just talk about the casting machining, so the conventional processes, so you have to design that particular process. But in additive manufacturing, you do not require to design anything. Okay, so over here you have to just create any CAD model, what means any complex object, or you can say, or any customized product. So that you can just do by using this additive manufacturing. Okay, so as a corollary to the first guideline, it is often possible to consolidate the parts, integrating features into the more complex parts and avoiding the assemblies issue. Then AM enable the usage of customized geometry and the parts by the direct production from the 3D data. So that basically you can just use this customized geometry in the additive manufacturing, that you can just do by direct production from the 3D data. Okay, so with the emergence of commercial multi-material AM machines, designers should explore the multifunctional part design that combine the geometric and the material complexity capabilities. Matlab, if we just require that as if we just talk about our body, so our body is having a different kind of the parts, and these parts are having some different kind of the functions. So this kind of the means, you can say, the functionality, or if you just require to create in any particular object, so you are requiring assembly of the different kind of the parts. But if you just require that these parts if can be manufactured by some common process or by some one process, so that can only be manufactured by the additive manufacturing, and the functionality is also retained over there. Means what functionality you just required, means suppose if we just talk about our legs, that legs is having the that requires some compressive strength and the fatigue, so we can just design over here. So AM allows the designers to ignore all of these constraints imposed by the conventional manufacturing process, although AM specific constraint and imposed. So exploring the design freedom. So in one approach, company have achieved the significant part consolidation, combining several parts in a single part. In second approach, researchers have demonstrated from how hierarchical structures can result from stretching the material in parts using the mesoscale or the microscale features to produce so-called the cellular materials. In the third approach, industrial designers have explored new design concept from some everyday products such as plates, chair, and the clothing. Then the parts consolidation, the redesign we just talked about. So the characteristic of the geometrical complexity and the suitable for the low volume production combined to the yield substantial benefits over there. And these are having some several significant advantages our design with multiple parts also. That is dedicated tooling for multiple part is not required over here. Okay, so finally it is often possible to design the consolidated part to perform the better than assemblies. Same with the hierarchical structure we just covered. The basic idea of the hierarchical structure is that the feature of one size scale can have the small feature added to them. Okay, so tailored, that you can just tailor the nano microstructure, the texture added to the surface of the part, and cellular material with the voids including forms, honeycombs. You can just, these are basically example of the hierarchical structures. Okay, industrial design application if we just talk about, so some very integrating approach to produce that design. Okay, a leader in this field was a small company that is the Netherlands called the FOC, that is the freedom of creation, that founded by this Tarun, which was the purchased by 3D system now. Okay, so these are basically the exploring the design freedom. Okay, so the example product, for as you can see that what you just required you can just design over here. So this is basically the reference book that is being written by the Ian Gibson, David Roshan, Brent Stucker, Additive Manufacturing Technology. You can just refer this book for the additive manufacturing, and the either if you just require some other complex topics, you can just refer this book. So thank you so much.